Hi, everyone. My name is Sergey Smirnov. I'm a senior technical specialist at Microsoft and Cosmos DB Global Black Belt team. And today we're going to talk about real-world NoSQL design patterns with Azure Cosmos DB. This is our agenda for today. We're going to discuss why NoSQL in general, what is Cosmos DB, Azure Cosmos DB, and how it relates to NoSQL database technologies. And then we're going to dive into NoSQL data model, design principles, best practices, and look at some real-world NoSQL design patterns and use cases and how we use Cosmos DB to solve them, as well as look at some lessons learned from solving large-scale customer challenges with Cosmos DB. So first thing first, NoSQL versus RDBMS. This is a very hot topic debate for many years recently as NoSQL technologies emerge. And the first thing we say is, whereas there is a big difference is, with NoSQL, it's positioned for high elastic throughput, especially for writes, because all relational databases use locks and latches to enforce asset semantics, and those usually are the blockers for scalability. NoSQL databases, on the other hand, use usually lock-free. They use quorum reads and writes and much simpler transaction concurrency rules, often based on optimistic concurrency. If you pair it with sharding data and distribution, you can achieve much higher and, more importantly, near linear predictable scalability and better elasticity. The other big difference is document storage. So hierarchical data document stores are often represented in NoSQL, and it fits in many data design patterns because they can be easily converted to simple hierarchical documents and use which is optimized for reads to avoid those expensive and often unpredictable joins by using embedding. And for referential integrity, you can still use referencing, and denormalizing data is totally okay for optimizing reads in NoSQL. Next big thing is fluid schema. Responding to schema changes in RDBMS systems over time often become challenging and time-consuming task, and viewed as a blocker to accelerating development cycles. NoSQL flexible schema design allow for much faster application development and schema version coexistence. And the last but not least is microservices, event-driven data stores. While you can still use data RDBMSs for microservices, they are designed as a big monolithic systems because they have big things embedded in the data stores. And microservices usually break down into smaller subsets of data where each microservice or each service owns its own data set. And along with that, they usually operate in JSON format for messaging, which naturally fits better in NoSQL store because of serialization patterns. And that's where it's better served for API-driven NoSQL databases. So now let's go into Cosmos DB, Azure Cosmos DB, and how it fits in the NoSQL world. Cosmos DB is a database for modern development with SLA-backed speed and availability, scalability, and open source APIs for many NoSQL engines. We have guaranteed speed at any scale. We have different SDKs and different APIs for different application developments. We are mission critical ready. We provide 5 nines availability with enterprise level security, and we are fully managed and cost effective to remove that M from RDBMSs. M stands for management, and we're trying to remove it and then take off that burden. So what is Azure Cosmos DB in a nutshell? We have multiple APIs for different type of workloads in NoSQL world because we're trying to be database fit for purpose. We have table API for key value, even though we can do key value with other APIs as well. We have Cassandra API for column family for Cassandra workloads. We have document type APIs for Mongo API, and also our core SQL API is also document type. They both store document JSON documents, and we have Graph API with Gremlin. All those APIs are based on foundationally on the same Azure Cosmos DB in the backend, and they all have the same guarantees and same SLAs behind the scenes and operate in the same principles. Common use cases solved with Azure Cosmos DB. We have many common use cases across different industries, but what you can see here is a pattern. We are very good with high volume event-driven systems like digital content management, order processing, shopping cart, inventory management, and it's a common across multiple systems. We also have another commonality is like Customer 360. Usually those are represented as embedded documents, which can usually modeled for serving high concurrency reads and represent for holistic view of your data. And like, for example, in healthcare, it could be Patient 360. In government, could be Citizen 360, but the same principle will apply. Let's look into NoSQL design principles and best practices. The first thing is we follow the base architecture, which means basic availability, soft state, and eventual consistency, which unlike ACID RDBMS type systems are relaxing the rules around it to allow for better scalability. We also follow duplication and denormalization of data as totally acceptable and often encouraged with NoSQL. Next thing is NoSQL database schema design encourages aggregating hierarchical data instead of splitting out elements that will later be joined and retrieved together using embedding, and duplicating data for documents which change frequently independently or have many-to-many relationship as a reference, and to deal with data relationship in NoSQL because there are still data relationships. We often use document type discriminator attributes to differentiate different documents. This is one of the best practices and often overlooked feature to take advantage of NoSQL. And last thing, partitioning and sharding your data for horizontal and flexible scalability. We believe in shared nesting architecture as a best scalability methods because your data is going to continue to grow over time, and it gives you that near linear and predictable scalability for your operations. If you combine it with those type discriminator attributes to collocate different type of documents which share same partition key, you can really take advantage of NoSQL world. So if we look into NoSQL data modeling best practices, data modeling in NoSQL is just important with relational data because there's still schema in NoSQL. It's just not enforced at database anymore. It is enforced, maybe not enforced as maybe a strong word, but you control that schema at the application level as part of your object model. And this is where the schema should live because it needs to be closer to application to remove that cycling of dependencies. Plan upfront for best performance manageability and more optimal cost. Smaller containers can add up to large dollars, and shared throughput can help, but it's still not ideal with many small containers because it still brings that manageability problem and oversubscribing to a degree. Smart data modeling can greatly help with optimizing cost and manageability, and we're going to look into some optimization tips and tricks, what you can do with it. So what we see in NoSQL data modeling, we see two extremes observed when customers try to start with NoSQL first. We see one extreme, normalize everything. This is where usually like we bring ORM type systems where they create a container collection per object, and if you have many objects, then you end up with too many containers. Or we have another extreme where we embed in everything as one piece just because we can in NoSQL. So ideally, you want to find a balance in combining both options in your design and find that happy medium, because usually the truth is somewhere in between. So let's look at, we mentioned the type attribute. Let's look at the more specific details. So many ORM frameworks by default use model one document object, one container. So this can easily lead to tens and hundreds of containers, even in relatively small implementation, which is not efficient. If you add a type attribute to your object models, often allow it to significantly reduce number of containers and collocate different type of documents in the same container where they use the same partition key, or you can even go further and create arbitrary partition key like PK attribute for partition key, and based on the type of document, assign the value for the PK. So in that example, for type vehicle, we can assign VIN as a partition key value, and for type package, we can assign package ID as a partition key value, and then we can collocate them in a same container. Another big thing with NoSQL data modeling is to know when to embed versus when to reference. So when to embed is usually you embed when you have one-to-one or one-to-few relationships. Set of values is bounded. When your data from entities is queried together, when you have child-parent dependencies, and when you have similar rates of updates for embedded data. Means that data doesn't change its much, and usually use embedding for better read performance. This is where, like the customer 360 view, you would probably do a lot of embeddings there, because there is a lot of reads on it's much heavier read patterns than write pattern. On the other side, when to reference, it's when you have one-to-many or many-to-many relationships, especially is like one-to-many is unbounded, where you likely will blow through partition limits, etc. And also when data change at different times and what's referenced, heavily referenced by many others. And we'll touch on one of those examples later in the slides. Usually it provides better write performance. So you're optimizing for minimizing the overhead for writes and updates. And there is a trade-off here to do multiple network calls and reads. Now let's look at some real-world NoSQL design patterns. One of them is distributed key value stores. Distributed key value stores use partition key and row key as a unique record ID to store and operate on row values. Partition key allow for horizontal scalability for high volume writes, and record key and ID will give you that uniqueness. It can be implemented with both Cosmos Table API and Core SQL API. But Core SQL API is preferred for new applications if you're not really migrating from Table API, because it gives you a little more flexibility on operations and also give you the additional benefits, and we'll look at the benefits later. It is schema agnostic. Different rows can have different collections or fields of attributes, so it's not necessarily have to conform in a specific schema, and this is power NoSQL. And the biggest benefit here is that it's very cheap point read operations by partition key and row key, or partition key and ID for SQL API. This is the cheapest operation you can get in Cosmos DB. It is definitely better scalability than blob tables, and additional flexibility for any occasional secondary field searches provided with Core SQL API, where you can mix point read key value lookups and simple SQL queries on key value stores with additional indexing and filters. Another big thing we want to stress is, which is a lot of times different from relational world, is IoT event stores and what they follow. So similar to key value stores, they often require high volume write throughput, but have additional requirements for filter and range, likely some aggregations. And those are best covered by Cosmos SQL API. Often those type of applications implement CQRS and event sourcing patterns to represent materialized view of data for read request and separate containers. So the example here is that we write data in one container, but we often may read data by the other partition key. So we need the different distribution of data. Or for example, in the other event sourcing example, with also CQRS, where we separate in the read and write path, we have materialized view of summary of the card instead of the basically as a snapshot. And this can be aggregated snapshot as well if you want to maintain it to optimize reads, because we don't want to recompute frequently. This often implemented with Cosmos DB with a feature called change feed, or some other event delivery solutions like Kafka or Event Hubs to have that near real-time updatable views of duplicated and aggregated data based on the query patterns. And this is query patterns is should be at the forefront of every NoSQL design, because while we scale to ingest writes, we also need to be cognizant about our query patterns, because we want our queries to be the fast. Ideally, you want to have a document representation of single query to single document to avoid multi-document reads or multiple API calls to get that representation in your API. From IoT document models, kind of like look into what we see as a patterns and how we can optimize things. We see two types of document models for IoT type elements. Single event data point used when ingesting data as a singleton IoT event as it arrives and create processed by single event. you would likely see a document represented on the left where you have ID, primary key, usually device ID, and then you have like source, timestamp, meter, unit, name, and value. Those are good when you actually ingest events as they come in through like event streams, and also you act on the event particular. We also see use cases with IoT where there is a lot of still decoupled IoT systems or event systems where they ingest data in batches, and they not really acting on the events in real time. So they more looking at the trends instead of real-time numbers. In that case, there is often more optimal way to convert the data, to pre-process the data before writing to Cosmos DB, to have either date-specific interval range if the intervals of the events are fixed value. For example, if we have per second intervals of my meter, I can create, instead of writing 60 documents, I can create one document with date interval start, interval duration, and then have a subset of data points for each second, for example. Or if the intervals are sparse, but we can batch them up and pre-process based on specific bucket of total values, I can then have date interval start, date interval end, have total values, and then have an array of the values as well. Like for example, we can move the even timestamps here if it's important to populate this way. Doing this can, like this particular example where we convert like per second events into one single document with 1 minute aggregations, not necessarily aggregations, but compactions, can save us about 3x in storage on a large data set and about 10x on more than 10x on our use. Because writing documents is expensive operation. And if we not look at per event operations, we often gonna read it in bulk anyway and process it downstream. Another key tidbits from real-world IoT event store implementations and best practices: optimizing partition key for majority of your workloads. IoT is often very heavy writes, and distributing them is more important probably than finding the optimal PK. Obviously, it depends on the use cases, but a lot of times this is actually the case. And we need to ensure that when we pick in the right partition key, we distribute the majority of the workload evenly across all physical partitions, because in IoT event stores, the size of the data matters. It's significantly large, and it's also overgrown over time. What we see in some cases is customers pick wrong partition key, and we tell them to avoid using timestamp date as PK. It's not really good for hashing, and it's often causing that round-robin hotspot partition or even internal auto-generated ID GUID are better PKs for write-heavy workloads. If you have a data, like based on your retention, you need to store data for device ID, and it will potentially exceed 20 gigabit limit, you can create composite synthetic partition keys with adding some kind of time bucket at the end, but it still need to be based on the high kernelity value like device ID. So just to give an example from, this is coming from one of the customers we help optimize. This is a graph of Cosmos normalized RUs, which was partitioned by the date. And you can see that majority of the work for 1 hour was on one partition key range, and then next hour it's jumped to the other partition key range. When we switch it to use the VIN number, we immediately reduce the workload from 40% to 3-4%, and we start using all partitions evenly. Another best practice is IoT stores accumulate a lot of raw data, which often does not use frequently past current date. Capacity can quickly get out of hand and lead to a lot of dollars and escalations and syncing it. So think of your data retention archiving strategy from day one. It's very important. And often IoT events data is also ETL to data lake blob storage to be used as raw staging data. And this is where we encourage you to look at Cosmos DB HTIP solution, where you can link Cosmos Analytical Store and Synapse Link to use the built-in replication capabilities avoid additional ETL. You can run operational reporting analytics on top of it, and also use you can take advantage of different TTLs on your transactional analytical stores for some long-term retention archival. This could allow you to significantly reduce the amount of data in your operational store beyond that immediate query need, and then for any and use analytical store for more cost-effective archival, and you can still restore and recover and roll back and load back the data if you need it through Spark. Last thing about the IoT event stores, if you have some frequent query patterns to get aggregate latest value, implement materialize view snapshot container and update it using change feed to only query last view of the data. So this is an example where you can do a select up one from the container where device ID 12345 order by timestamp descending. This will give you a last snapshot of the event, basically last state of the event. But if you have a lot of data there, that query can be somewhat expensive. And if concurrency of the type of query is higher than the cost of the update, it would definitely make sense to create a secondary container with a single document per device. And you would use change feed to basically update the document. And maybe if you need to pre-compute some averages, which can be even more expensive in the queries, and use it for read pass to basically separate the write and read pass, and also have that aggregations. Which is another example here. If you have query patterns which you use to aggregate, to run some aggregate functions on multiple equality on range filters, you definitely recommend to look at Cosmos composite indexes. I'm including the link to an excellent dev blog post by our own team Sander from Cosmos product team, which describes the use cases for composite indexes. This is an example from one of the customers we help troubleshoot and reduce consumption using composite indexes. That was the example of the query where the recurrence star from device from the container by the device ID and the timestamp ranges and some type predicate. And that query was only returning 7 documents. Device ID was partition key. There was nothing wrong there. And all the documents were small, so it was 5 kilobyte total payload. But that query was astonishing 700 RUs. The reason for that is because of that significant range of timestamps cardinality coming from index paired with a high cardinality for device IDs. Compute cost of the query was significant. When we added the composite index, we reduced RU charge for the query down to 3.5 and significantly reduced the amount of stress on that Cosmos collection, allowed to save a lot of money. Next topic we're going to look at is large hierarchical document modeling. So even with just a few levels of, so normally we would use embedding as a recommended solution there, but we need to take it with a grain of salt, because even with just a few levels of hierarchy, documents often balloon in size, and this is where we're telling you, watch out for max document size, because if, for example, this is an audit document for a large, let's say, Fortune 100 company, where we have audit header, and then we have audit tasks, and then for each task we have multiple task steps with the results. And I'm simplifying this, but the results could be multi-kilobyte references, and there could be hundreds of tasks, etc. So that document can quickly become not just a big document, but very expensive from maintaining the document, because each of those tasks will be executed, and the document needs to be updated in parallel by multiple threads, constantly overriding it. And that definitely will be a very expensive operation on the large documents, and also will cause probably a latency spikes as well. So recommended solution would be here to split the document at each hierarchy level by level type, and partition collocate them on the same high-level partition key, say company ID, which is at the highest level. This is where you can take advantage of our Cosmos DB asset transactional consistency if needed for operations in multiple documents with same partition key scope. You can use as a store procedures or transactional batch, and you can still retrieve documents to build your hierarchy on the query side. Basically, if you select from the container where partition key would be company ID, order by level type, ascending, descending, or however you want to do it. You can even do sub-selects, like where you can do like and level type in to put specific tasks, for example. And you can also do a sub-level task selections here as well. And you would use deduplication of reference IDs of related level type documents, like task embed task ID name into task results, task activities, embed other things from the higher levels downstream for linking them together. Let's next section, we're gonna look into best practices for large data loads migrations into Cosmos DB. This has often lately become a hot topic because a lot of customers migrating significant amount of data, terabytes, 110 tens and maybe dozens of terabytes, multiples of 10 terabytes up to 100 terabytes. And large database load migrations require planning and size throughput estimates, and Cosmos DB knows section. We can still ingest the data if you don't plan for it appropriately, but behind the scenes, we'll be doing preemptive physical partition splits as data loaded in, and partition splits is a resource-intensive operation, and you would want to avoid this during the big data load because you're essentially competing for the same resource, and taking the RUs to do partition splits from the load operations, which will result in dips in your throughput and eventually longer load time. So if you spend some time upfront to estimate your target data size and pre-create container, basically estimate the total size, convert it to number of partition, and pre-create container with a targeted number of physical partitions upfront, you can optimize resources and allow to achieve that desired targeted throughput accurately. You need to do 3 things to get 3 things to do that estimation. Get average JSON document size, estimate total number of documents to be loaded or migrated, and in ballpark, define desired duration of migration. And then you can evaluate it versus what would be optimal one, and then you can adjust it accordingly. So now I'm going to walk through the process and show you some examples. So the step 1, find total target size of the loaded data. Basically, take your average document size, multiply by number of docs, get total size in gigabytes. Step 2, convert that number of gigabytes into number of physical partitions in Cosmos. And this is where we're going to share some internals. Right now, maximum partition size is 50 gigabyte. And for estimation, we recommend you to use about 40 gigabyte per partition to allow some room for indexing, for a further partition grow, to avoid the partition splits as soon as you finish the loads. So once you get this, the next step is estimate the RUs needed to pre-create Cosmos database container based on that number of partitions. So this is, you have 2 choices, depends on what type of provision and throughput you're going to use. Whether you use manual, if you use manual, the rule would be number of physical partitions times 6,000. If you use autoscale, it would be number of physical partitions times 10,000. And that's what I'm using in my example. And the final step is estimate per document write RUs, and then based on that, calculate load duration throughput. To estimate per document write RUs, you can use either write RU charge. We have multiple ways to find it, or you can simply use Cosmos database capacity calculator. So I'm going to show you some trick here. This is a capacity calculator, and you have a choice of either specifying the size, where you can say you load in 100 key document and you change your create to 1. You can do calculate, and it's going to tell you roughly what the RU for creates would be, and you can use this for estimates. The more effective way is to upload sample JSON document. So if you pick your JSON document and recalculate, it will actually do a single write, and it will calculate RUs based on your particular document size. The other thing is you can, so by default, it's using disabled index policy, and you can do it to optimize bulk writes. You can also use either automatic or custom index policy to estimate if you know what your query filters are, to know exactly what the RUs would be for specific indexes. For example, you need to know that there is indexes overhead. So for example, if I choose automatic, means that I'm going to index all the properties instead of just an ID. For the same document, my RUs is going to become 14 because I have a handful of properties there, and if I'm going to index all of them, I need to account for RU overhead for this. Then you can simply take this RU charge and estimate throughput based on basically dividing your max RUs for autoscale for provision container to document write RUs to get the estimated throughput per second, because RUs are per second. So based on this, now you have your estimated throughput, and this would be your most optimal throughput based on your target size. And you can compare that with your projected estimate throughput, basically what you expect or what you want to achieve, and then adjust if needed. Like for example, if you're not matching, you definitely need more RUs. So you would pre-create collections with more partitions and then scale it down further, because the last thing you want to do at the end is scale down. For scaling down, we want to be aware of minimums for scale down. Minimum is usually a function of three things, and it's a little different between the manual and autoscale. So for manual, and the difference is primarily because autoscale defined you the 10x range for bursting. So the function is basically a max of the three things, 400, maximum throughput provision divided by 100, and current storage times 10 RU per gigabyte. The last portion of the minimums, the storage times 10 RU per gigabyte, will go away soon. And right now we have a way to remove this on per account basis. If you have terabytes of data and you have low throughput volumes for scaling down after big loads, if you simply just subscribe to our high storage, low throughput program to allow for better RU cost management. So essentially, it will become 400 versus or max throughput provision divided by 100. So if we take all those steps and the formulas and look at the best practices and an example, let's work through how it looks with some numbers. If we take our doc size of 1 kilobyte and we estimate that it's about 5 RUs per write, and we want to load 1 billion documents, which will roughly become 1 terabyte of data, and we want to load in about 10 hours. So 10 hours, for 10 hours load, we roughly need about 28,000 writes per second to estimated throughput. So based on our total document size and total size of the container, we need about 25 partitions based on the 40 gig per partition, which means that we need to pre-create container with 250,000 RUs for autoscale. And based on this, our throughput estimate would be about 50,000, which means that we can actually achieve our load in about 5 hours based on that estimate. And once the load is done, we can scale down to 100,000 autoscale, which will give us a 10,000 to 100,000 range. And if we need to scale down even further, we can, like our absolute minimum scale down would be 2,500. Last thing we want to touch is estimate the overhead of the cross-partition queries. So we often discourage from using cross-partition queries as they do not scale efficiently, but they may be okay for specific use cases, and often depends on your data set. So the one thing we want to, so it's more importantly here is to know what is the actual impact and how to estimate it without having the millions of records of data. So you can use the same functions as and same estimate process we described earlier to estimate the process, to basically figure out number of partitions you need for your total data set, but preload it with just a sample of data, which is representative for cardinality, but not necessarily for the full volume. So in that example, I have container partition by ID, and I have a simple query where I'm selecting star from that container where I'm filtering by non-partition key customer ID. And my query returns 10 document with about 1 kilobyte per document. So let's jump here, and I'm going to show you the demo. So we're going to run that query on a container where I only have one partition. So I only have 3.2 RUs for the query stats. And you can actually see how many partitions I'm touching if you look at the query per partition query metrics. So you'll see that I'm only touching one partition and one row. Now I'm gonna look at the collection with 2 partitions and run the same query again. And look at the query stats. Now it becomes 6 RUs. So I'm seeing that somewhat nearly linear increase in RU cost. With 2 partitions, again, I should be able to validate it here. And now I'm gonna run it again on collection with 10 partitions, because 10 partitions would represent my total data size. And let's look at query stats. Now my query stats is about 28.3 RUs, which is close to, we can see the same trend, and we can see a per partition query metrics as well, where we should see 10 records with fan out query for each partition. And you can see that this are 10 records, and actually based on that ID, it's only hashed about half of them. So only touching technically half of them, even though I have to probe the other ones, even though they don't have data. So this can give me some assumptions and projections on what that partition impact would be, and I can use it to project and evaluate those queries if needed based on the query concurrency and the patterns, right? So you can see that for one partition, I can have up to 50 million doc, assuming that small doc size, and up to 10,000 RUs, 50 gig, with 10 physical partitions. My collection can be up to 500 gig with 100,000 RUs and about 500 million docs, which is pretty big number, but it's still fairly reasonable, right? So that's, if it's not the most highly concurrent query, and if there is no frequent updates on this, we can probably use it as well for some occasional cross-partition queries, and this should be our expectation. So with that, we getting close to the wrap. So I want to summarize our review today in a few takeaways. So the first thing is use base CQRS event-based architectures core principles when you're designing your system with NoSQL. Model your documents and choose partition key based on your workloads. Use that 80-20 rule to optimize for majority and try to ensure linear scalability for your top queries. And also try to avoid anti-patterns. Then know and profile your workload and queries. This is essential for optimal NoSQL design and the best performance. And the last, known physical boundaries of your data workloads can help you plan and optimize it more efficiently. With that, I'm gonna finish my presentation, and you can enjoy the rest of the conference. Thank you.